is an introduction to linear functions. A linear function is a specific type of function that can be written in one of those forms, y equals mx plus b, or f of x equals mx plus b, which means the same thing because f of x is just another way of saying y. And you'll be asked to identify whether the function you're given is linear or not linear just by looking at it. So this first one, y plus 1 equals negative 2x, I can see that it's going to be linear. I'm going to rearrange it on paper to put it in the correct order, y equals negative 2x minus 1. So you can see it's now in the correct order, y equals mx plus b. And this is a linear function. The m is negative 2 and the b is negative 1. The next example, f of x equals x minus 1 minus x to the third power. You can see in y equals mx plus b, we don't have any exponents anywhere in there. That's because in a linear function, the highest exponent is a 1. And it's not shown when the exponent is a 1. So as soon as you see an exponent in your function other than 1, you automatically know that it's not linear. You don't need to do any rearranging to show that it's not linear. And the last example looks linear. It doesn't have any exponents in it that are higher than a 1. There is an invisible 1 on that x. And I'll just put it in the correct order to show that it can be written in the form f of x equals mx plus b. I'm just rearranging the right side of the equation to show that that is linear. And there's one more common example. It's not on this slide, so I'll write it in. Y equals, let's say, 2 divided by x plus some constant. If you have 2 divided by x, it almost looks linear because it almost looks like y equals mx plus b. But in a linear function, m is being multiplied by x, not divided by x. As soon as you have x on the bottom of a fraction, that also makes this not a linear function. Now we have a graph. Let's look at what linear functions look like on a graph. So for a linear function, each input is going to yield a specific output, and the set of those pairs, those points, is going to form a line when we connect them. So the function y equals negative 2x plus 5. I can represent that as a list of ordered pairs, and it doesn't tell me anything specific for x. So when I'm trying to come up with some ordered pairs, I can really use anything for x. And in fact, that table could go on forever, but I don't need an infinite number of points to make a line. I really just need 2 or 3. I'm going to use 3 here. I'm going to use a negative value for my input. I'm going to use 0, and I'm going to use a positive value. Those are the easiest 3 numbers to use to make a line. So we'll use those as our 3 inputs. And like I said, it could go on forever. I could use more points, dot, 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 but I don't need to. So I'm going to plug in negative 1 in place of x in the function. So what I'm doing, and normally I don't show this step, but I'll show it here so you know. I am replacing the x from my function with my input value, and then I'm going to simplify that. So negative 2 times negative 1, add 5 equals 7. Replace with a 0, which is going to equal 5. And replace x with a 1, which is going to equal 3. And because my x values were following a pattern, my y values are also following a pattern, as you can see. I'm going to put these 3 ordered pairs on my graph. Now, the ordered pairs are the pairs of input-output values. And you know each pair is a point on the graph. Each one is x comma y. So to graph these, I'm going to find negative 1, 7, put a point at it. Find 0, 5, put a point at it. Find 1, 3, and put a point at it. And then connect my dots. Because this table could go on forever, that line goes on forever. So don't stop at the end of your points. Put an arrow in one direction and an arrow in the other to show that that line goes on forever in both directions, even though you're only using those 3 points to show where the line appears. And that is the graph of the function y equals negative 2x plus 5. Now, the domain of a function can be limited or restricted if it's shown. Okay, so in the first example here, it says graph the discrete function for the given domain. So discrete just means it's going to give you some specific points, and those points are not to be connected. So a discrete function, it doesn't happen that often, but if you see that word discrete, it means show each point separately and discretely, but don't connect the dots into any kind of curve or line. Just show the points. And they're giving me specific points to use here. So when I make my input-output table, my input values specifically are negative 2, negative 1, and 0. That is the function they want me to show here. plug in -2, -1, and 0 into that function, y equals 2x plus 3. And we'll come out with -1 as our first output, 1 as our second output, and 3 as our last output. Those 3 points are going to go on the graph. -2, -1. Oops. Put that in the wrong place. -2, -1. -1, +1, and 0, 3. As tempting as it is to connect those into a straight line, I'm not going to because I see that we're discrete. So that's the graph of the function. In the second example, it says graph the continuous function. Now that is when we're going to connect the dots to make a line or a curve or a shape. And you don't always see the word continuous. If you don't see either discrete or continuous, it usually means continuous. But I'm showing you those two words so you can see the contrast between them. And this time, our domain is x values that are less than 3. Now you might see something like x less than or equal to 3. We don't see that here, but that's the other symbol that's sometimes used, or greater than. Since it doesn't have an equal sign in our example, that means we're not actually going to use the value of 3 on our graph. So when I make my input-output table, I'll include 3 so I know the first point that I'm starting from without including that point. And then I'm going to include values less than that, so 2 and 1. Plug those into the function. We're going to get -3 as our first output, 0 as our next output, and 3 as our other output. And when I go over to the graph, I'm going to do something interesting with that first point. Because I am not supposed to include the 3, when I find the point that's located at 3, I'm going to put an open circle there to show that I'm beginning from there, but not including that point. And then the other points, 2, 0, and 1, 3, can be solid points. That's the direction my graph is going. And it would continue on forever in that direction. So I will put an arrow in that direction and not go past my open circle. And that's the graph of the continuous function for that specific domain. That is all.